Alright, so we're going to define one of the coolest things in this course, and it's going to be essential for the rest of this topic. It's going to be a crucial tool that's going to allow us to do a lot, and that's the gradient vector. And so let me give a little bit of motivation of where this is even coming from. So let's suppose that we have a function of two variables, x and y, and so our domain of our function is going to be some subset of the xy plane. So it's important to realize that when you see this xy coordinate system, I'm not actually going to be plotting a function on here. This is actually going to be something in the domain. Now what I can do is define level curves and draw level curves on my coordinate axes in the domain of my function f. So let's say I have some kind of level curve like this. I'm just going to draw something strange. So this is like maybe f is equal to 0. So these are all the values in the domain of my function that give me an output of 0. That's a level curve. And so we can keep going. Maybe we have something else like this. I don't know. Maybe this is f equals 1. And then maybe we have some more level curves, one right here and one right here, and so on. Maybe that's f equals 2, but that's the idea. So you kind of get this sense that this is lower elevation out here, and we're kind of going in to higher elevation over here. All right, so if I pick a point somewhere in the domain of my function, let's say right here, now what I can do is I can define the partial derivatives. So f sub x and f sub y. Now what f sub x and f sub y actually are telling me geometrically is the rate of change of the function if I cut the function along a plane parallel to the x-axis and a parallel to a plane parallel to the y-axis, like that. So these are actually giving me the rates of change in these two directions. Now there's nothing really special about the x direction and the y direction. I could think about taking the rate of change of the function if I cut along this direction or this direction. Wherever I wanted to find sort of how is my elevation of my function changing in that direction, well, I can do that. And the way I do that is I'm going to use this gradient vector. But the gradient vector is going to do something very cool for us. So let me just tell you what the gradient vector is. So the gradient vector of a function of two variables, and we'll have a similar definition for functions of more than two variables, but we'll start just with the function of two variables, is denoted by this crazy looking upside down triangle, f. And now this, just a side note, this triangle thing is called nabla. Okay, and it's a Greek word that describes sort of an ancient Hebrew harp, and it sort of looks like a harp if you've seen a harp. But what it means for us is it's the gradient. So it's a vector. It has an x component and a y component. The x component, put simply, is the partial derivative with respect to x, and the y component is the partial derivative with respect to y. And now notice that this is going to be a function of x and y here. And it may be that there are certain points where the gradient function doesn't exist. If, say, the partial derivative with respect to x doesn't exist, or the partial derivative with respect to y doesn't exist. But when it does exist, I can evaluate. So if this is some point AB, well then I can talk about the gradient of the function evaluated at the point AB. And so what is this? Here it is. Here's the definition. So I just put the x component, or the partial derivative with respect to x in the x component, partial derivative with respect to y in the y component. But what is this vector at some point? Well, this vector is going to point in a specific direction. It points in the direction of steepest ascent. Okay, so what do I mean by that? Well, let's say I'm at this point here. So where does the gradient vector point? So notice that this is on a level curve corresponding to f equaling 0. And so the uphill direction is this way. This is like the top of a hill up here. So the gradient vector is going to point basically straight uphill in the direction of steepest ascent. So if I'm climbing a mountain and I say, all right, what's the most direct path to the summit? Well, I just want to aim straight uphill in the direction that's actually the steepest. And so if I pick another point, so here's gradient of f right there. So if I pick another point right here, the gradient vector is going to point straight uphill. Or if I go, say, here, gradient vector is going to point straight uphill. Or over here, the gradient vector will point straight uphill. And there's another important property. So it points in the direction of steepest ascent, but also if I take some point AB and I look at the gradient vector, it's going to be orthogonal. Just remember that means perpendicular to the level curve. And we're going to use this fact later when we define the tangent plane. So what I mean is, if we look here at the gradient at this point, well, it's going to be perpendicular to the level curve, like that. So in other words, if I take a direction that's pointing in the direction of my level curve, well, the gradient is going to be pointing in a direction that's perpendicular to that direction. So these are just two of the most important properties of the gradient. Okay, so geometrically it points in the direction of steepest ascent, but maybe a little bit more technically, it's orthogonal to the level curve, and that's going to be extremely important. So let's just make a couple notes about the gradient. So first thing, we define the gradient for a function of 2 variables. But for a function of, say, 3 variables, we can also define the gradient vector. And you can probably guess what it's going to be. It's going to be the vector. It's now going to have 3 components. The x component is going to be the partial derivative with respect to x. The y component will be the partial with respect to y. And the z component will be the partial with respect to z. And we don't have quite as nice of kind of a geometric interpretation as the direction of steepest ascent, but the gradient vector points in general in the direction of greatest change. And now notice I'm not using steepest ascent anymore because we don't have quite the geometric way of visualizing greatest change as steepest ascent, but the gradient will point in the direction of greatest change. So that's the first thing. And then secondly, the gradient will be orthogonal. Well, we don't have level curves in 3 dimensions, we have level surfaces, but the gradient vector in 3 dimensions will be orthogonal to the level surface. Which is really cool. Okay, great. Okay, so let's talk about a really cool application of the gradient vector. So we said the gradient vector points in the direction of steepest ascent or greatest change. But let's say we have f, a function of two or more variables, and u, a vector. Then we define what's called the directional derivative of f in the direction of u as follows. So of course we're going to assume that f is differentiable at the point where we're defining this, because what we want to do is we want to take the gradient of f. So the notation is d sub u of the function f. And now what this is we take the gradient of f, and project it into the u direction. And what we really do is we just take the scalar projection of the gradient in the direction of u. So it's a dot product of the gradient with vector u divided by the length of u, and this really is just the component of the gradient that lies in the direction of u. And so there's another way to think about the directional derivative that's very helpful. So if the gradient points in the direction of greatest change, then the directional derivative is really nothing more than the rate of change in the direction of u. So we can think about it this way. If I take a step in the u direction, then the directional derivative tells me by approximately how much my function is going to change in that direction. All right, so we're going to continue talking about functions of just two variables. And it's important to remember that all of these ideas will extend to functions of three variables or functions of more variables, but the mantra is if you can understand it in two dimensions, then you'll be golden. You'll be able to sort of just adapt the ideas to higher dimensions. So suppose we have a function of two variables, and we've talked about several things involving the derivative. We've talked about the partial derivative with respect to x, and now we can think about this as the directional derivative in the x direction. We've talked about the partial with respect to y. This is the directional derivative in the y direction. We've talked about the gradient of f. This is the directional derivative that's actually in the direction of greatest change. Okay, so if you're at a point, you want to know which way do I go to have the function increase the most. That's what the gradient is going to give, which is going to be very helpful for lots of different things. But actually for now, the gradient of a function in sort of a unique way is going to give us a way to actually just nail down what it means for a function to be differentiable at a point. Okay, so in one variable, let me just remind you, a function is differentiable. So f of x is differentiable at some point x equals a if, well, this limit exists, basically. So the limit as x approaches a, f of x minus f of a over x minus a exists. Okay, so we've already seen that it's a lot more complicated, even just in two variables. Because remember, to check if this limit exists, we kind of want to check from the left and from the right. So a limit will exist if the left-hand limit equals the right-hand limit. But in more than one variable, say in two variables, there's actually infinitely many directions that we have to check and make sure this sort of rate of change exists. Here's three of them. We have the partial with respect to x, the partial with respect to y. We have the gradient is going to be one of those directions. And so we could just go through and check all those infinitely many directions. But that's really inefficient. And what's really happening is, if you think about all these infinitely many directions at a point, we're really filling out not a tangent line like in one variable, but a tangent plane. So in two variables, the idea is going to be that a function is differentiable here again we're in two variables, so at some point in the plane, if f has a tangent plane at this point, AB. So in other words, another way to say that this function has a tangent plane AB is to say it has a linear approximation. And this is really connecting back to the one variable case, because for the derivative to exist in the one variable case, we also needed to have a tangent line, and we had the interpretation that the derivative was the slope of that tangent line. Okay, now we're in two variables. We have a lot more direction. Well, what is a linear approximation of a function of two variables? Well, it's not a tangent line, it's a tangent plane. So if we have a tangent plane approximation, then this function is said to be differentiable. Okay, and I realize that I haven't really given you a way to find a tangent plane or anything like that, but I just want to make this connection that differentiability is really related to this idea of a linear approximation at a point. And in two variables, that's going to be a plane. And again, this idea will generalize to multiple dimensions, more variables other than two. But if you can understand it in two variables, then you're on your way to understanding the idea of differentiability. Okay, so I'm going to do my best here to sort of give you a visualization of the tangent plane. And I hope this really isn't coming out of nowhere. I hope it's very natural when you see this. So we have our XYZ coordinate system. And so I'm going to draw our function here. So our function of two variables is going to be some kind of surface like this. Okay, hopefully you can visualize that. It's going to be curved, right, in general. I mean, it could be a plane, it could be flat. But here's kind of our function plotted here, and it's going to be plotted kind of above the xy plane. So here's our domain down here, and here's the surface that's being formed or being graphed by this function here. And so if I take a point say right here, now we already talked about that in any given direction there could be tangent lines, but sort of the collection of all those lines will live in a plane like that, and that plane is going to be tangent to the surface. And if you can't visualize this, take like a basketball and a piece of cardboard and put the the piece of cardboard on the basketball and have the cardboard just touch the basketball at one point, and that will be a representation. You have the basketball is the surface, and then that piece of cardboard will be the tangent plane. Okay, so hopefully you're kind of tracking with this idea of tangent plane. So let's talk about how we would actually find a tangent plane. And again, if we can find a tangent plane, that means our function is differentiable there, or it has a linear approximation there. And a lot of times you'll want to use that linear approximation to sort of estimate function values, just like you did in one variable. Okay, so here's what we do. We know that z can be written as function of xy if we have a function of two variables. So in other words, we can plot our z-coordinate to be just the scalar output of our function of two variables. Here's what I'm going to do. I'm going to define a new function of three variables. Okay, and it's going to be f of xy minus z. Okay, and so this looks a little weird, but why did I do this? Notice that our surface, or the graph, of f is the level surface capital F equals 0. Okay, so now maybe you see the connection. I'm sort of giving a generalization of our function. I'm saying our function is just one of the level surfaces of this function of three variables. Okay, and why am I doing this? Well, I'm going to skip some of the technical details, but assuming that our derivative, or our function f has continuous partial derivatives, I think that's all we need. Well, what is that going to allow us to do? It's going to allow us to form the tangent plane at any point. So at the point A, B, if I take the gradient of capital F and evaluate it at, well, A, B, and then I need to evaluate it at a z-coordinate, well, I'm just going to evaluate it at the z-coordinate that's going to be on this level surface, or in other words, just f evaluated at AB. So the z-coordinate of the function. So this gradient is orthogonal, so we already saw this, to the surface, to the level surface, f equals 0, but to the surface, z equals f of xy, hence orthogonal to the tangent plane. At this point AB. But this is amazing, right? Because how do we describe a plane? Well, to describe a plane, we just need a point on the plane. But this is our point on the plane, right here. We know the plane is going to touch the surface at this point. You know, just think about the basketball example. At that one point on our surface, our plane is going to touch. And then this gradient vector is going to be our vector that's orthogonal to the plane. So that's going to allow us to write down the equation of the plane. But then that's easy. All we have to do is just say, well, let's call this vector n. Okay, this is just some vector. I can just plug in the numbers. And so I just take my vector n, and I take the dot product with x minus a, y minus b, and z minus f of ab. And I set that equal to 0. And this is my equation of the plane tangent to my surface, the graph of my function, at this point AB. Okay, so now that you've listened to me give a little bit of background on the tangent plane and differentiability, let me sort of give you the final answer. So if I want the equation of the tangent plane, so the tangent plane of a function at a point AB is just, well, if what I had on the last slide, that dot product, if I expand it out, this is what I get. I get f of x evaluated at AB, so the partial of f with respect to x evaluated at that point, times x minus a, plus partial with respect to y evaluated at AB, times y minus b, and then plus f of AB. So this is almost identical to the linear approximation in one variable. Recall that it's f prime of a, so this is the one variable case, times x minus a plus f of a. So you see all we've done is added in the change in the y direction. So we have the change in the x direction, the change in the y direction, and as long as these partial derivatives are continuous, this tangent plane will be tangent to the surface, and we can say that the function is differentiable there. Same thing we can do in one variable. If we have more than two variables, well, imagine what we're going to do. We're just going to add on more and more terms. We're going to have an fz evaluated at the point times a z minus whatever c point that is. So this idea is called, so this tangent, finding the tangent plane, or in one variable the tangent line, this is also called finding a linear approximation. To f at the point AB. And this is very useful in practice because, you probably remember this from the one variable case. Maybe you have a function, you don't really know much about the function, but if you can find some sort of linear approximation, then it's really easy to approximate nearby values of the function. So this is extremely important in just basic function approximation theory, this linear approximation. And that's what the tangent plane really is. And here is sort of the cookie cutter definition that, if you just want to plug and chug into, that's the tangent plane. Okay, so we want to find the gradient of the following function and then evaluate it at the point that we see here. Okay, so recall that the gradient of a function f is the partial derivative with respect to x, and then the partial derivative with respect to y, like that. Well, for a function of two variables. If there are three variables, we would have another component that would be the partial with respect to z. So notice that the partial with respect to x is going to be natural log of y, and then the partial with respect to y, now this is still a function of x and y, later we'll evaluate it at this point, but the partial with respect to y, we just treat x as a constant, take the derivative of log y, which is 1 over y, so it should be x over y. Okay, so then the gradient of f is just natural log of y, that's the x component, and then x over y is the y component. And then if we evaluate at the point 1, comma, e, then we get, well, natural log of e is 1, and then 1 over e. And so recall, just to reiterate, that so I don't really know what this function looks like, but maybe here's some of these level surfaces, whatever. And so wherever 1 over e is, let's say it's right here, or sorry, 1 comma e, this is not to scale, but I'm just showing you that this gradient vector right here is pointing in the direction of greatest change. So here's our level curve where the function doesn't change along that level curve. So it's sort of pointing uphill. So this is going to be the direction of greatest ascent if these level curves are kind of representing going uphill like that. All right, so now we're going to take the gradient of this function. Notice that it is a function of three variables. So our gradient is going to be partial with respect to x is going to be the x component, partial with respect to y is the y component, and then partial with respect to z is the z component. Like that. Okay, so let's just see what all of these things are. So the partial with respect to x is going to be y squared. Remember, y and z we just want to treat as constants, plus z fy is, okay, 2xy plus z squared, and then fz is going to be, okay, so 2yz plus x. Okay, I know that's pretty dry. But now we want to just, okay, so to find the gradient, these are all of the components, but we want to actually evaluate this gradient function, vector function, at this point 2, 1, 0. So fx of 2, 1, 0, well, that's just going to be 1 plus 0. Fy of 2, 1, 0 is going to be 2 times 2 times 1, so 4 plus 0, so 4. And then fz, evaluated at 2, 1, 0, is 2 times 1 times 0, so 0, and then plus 2. So the gradient evaluated at the point 2, 1, 0 is the vector 1, 4, 2. Okay, so we want to determine the rate of change of this function at the given point in the direction of u. And so what this is really asking for is the directional derivative of f at this point in the direction of this vector. So recall what this means. Well, we just want the scalar projection of the gradient of f at this point in the direction of u. So that's just going to be the gradient of f evaluated at 1, 0. And then we do the dot product with the vector u, which let's just write what that is 1, 2. And then we want to divide by the length of our vector u, which is the square root of 1 squared plus 2 squared. So again, this is just the gradient projected onto the u direction. And that's what we get. So what is the gradient of f? Well, the gradient of f is sine y, partial with respect to x, and then partial with respect to y is x cosine y. And then evaluating the gradient at the point 1, 0, we get 0. Cosine of 0 is 1 times 1 is 1. So the rate of change in the direction of 1, 2, or in other words, the directional derivative of f in this direction, is just 0, 1 dot 1, 2 over square root of 5, but this is just 2 divided by the square root of 5, because 0 times 1 plus 1 times 2 is 2, and there we have it. All right, so remember again, we're trying to find the rate of change of this function at this point in the direction of this vector. So in other words, we want the scalar projection of the gradient at this point onto this vector. So just writing that down symbolically, what we want to take the gradient evaluated at the point 1, 1, 1, and then take that scalar projection, or how much of the gradient lies in the direction of this vector 1, 1, 1, divided by the length of this vector 1, 1, 1. So again, this is the scalar projection of the gradient at this point onto the vector 1, 1, 1. Yeah, so what is the gradient? That's our first question. Well, partial with respect to x is y squared z cubed. Partial with respect to y is 2xy z cubed. And then partial with respect to z is 3xy squared z squared. And then if I evaluate at 1, 1, 1, well, this is just going to be 1, 2, 3. Perfect. Okay, so now let's go in and actually fill in what this vector is. So it's 1, 2, 3 dot 1, 1, 1 divided by the length of this vector, which is the square root of 1 squared plus 1 squared plus 1 squared. And what is this? This is 1 plus 2 plus 3, 6, divided by square root of 3. So that's the rate of change, or the approximate amount the function will change when we take a step in this direction. Okay, so we want to find the equation of the plane tangent to the graph of this surface. Okay, so this is basically a function of two variables just being plotted as a z-coordinate in three-dimensional space, and then at this point, so specifically at the 0.11 and then f of 1, 1, we're going to have a tangent plane, and we just want to find the equation of that tangent plane. So if you listen to the lecture, there's sort of a long drawn out way you could think about how to find the tangent plane with the gradient vector of this function of 3 variables, but then we ended up with a really nice formula. So the tangent plane, it's actually really nice. So you just take the change in x at that point and then multiply by, well, basically how far you are away from that point, and then plus the change in y at that point times how far you are away from the y-coordinate, and then you just translate up by wherever you are in the z-coordinate. So it's very much analogous to the tangent line. You know, if you're just in one variable, of course you would only have the change in x times how far you are away from x plus the function value there. So it should be very natural. It's a very natural extension of the tangent line equation. So let's actually figure out what fx is. So the partial of f, and again, I'm just saying z is this function of xy. And so maybe there's a little ambiguity about this c with this function and this c with the tangent plane, but that's okay. So the partial with respect to x of this function is just 2x. The partial with respect to y is going to be 8y. So if I evaluate the partial with respect to x at the point 1, 1, I get 2. And if I evaluate the partial with respect to y at the point 1, 1, I get 8. Great. And so now let me just plug that in. So I have z is equal to 2 times x minus 1 plus 8 times y minus 1. And then plus f of 1, 1, well, that's just the function evaluated at 1, 1. That's 1 plus 4, which is 5. So this is the equation. Of course, it's the equation of a plane, but specifically, it's the plane that's tangent to the surface at this point. So really cool stuff. Okay, so we want to use a linearization, or in other words, a tangent plane approximation, to approximate this number. And now the first thing you should think is, well, I know how to find the tangent plane of a point of a function of 2 variables, but where's my function of 2 variables? Well, this is where we actually have to do a little bit of thinking and say, well, let's let our function be, well, this is the square root of something a little bit more than 3. So we'll just say that's x squared. And then this is plus something a little bit bigger than, or sorry, a little bit smaller than 4. So we'll just let that be y. And notice that what I want is f of 3.1, 3.9. And of course, we could just throw that in a calculator, but we want to get an approximate value. So I have this quantity, what is it approximately? And I want to do this just using pen and paper. If I could use a calculator, there's no point in doing this. So we're kind of doing it old school. So here, what are we going to do? Well, we're going to find the linear approximation, or the tangent plane, at a special point. And of course, I want my point to be pretty close to the point 3.1, 3.9, but I hope that I can pick a point close to that point that's easy to evaluate in my function. Well, the point that I'm going to choose is 3, 4. And now why is that? Because what happens if I plug in x equals 3 and y equals 4? Well, this is 9 plus 16, which is 25. The square root of 25 is 5. So that's easy to evaluate. So what do we need for the tangent plane? Well, we need the partials. So the partial with respect to x is going to be x over square root of x squared plus y squared. Just a little bit of chain rule. Fy is going to be y over square root of x squared plus y squared. And if I evaluate at the point 3, 4, notice that I get 3/5. If I evaluate the partial with respect to y at 3/4, at 3, 4, I get 4/5. And notice that we already said f of 3, 4 is 5. So the tangent plane is going to be, well, the change in x, which is 3/5, times x minus 3, plus the change in y, rate of change in y, times y minus 4, and then plus the function value at 3, 4, which is 5. So there's the tangent plane, and now I want to use this tangent plane, or the linearization, to approximate this value. So let me just plug in 3.1 for x and 3.9 for y. So if I plug that in, I get 3/5 times 3.1 minus 3 plus 4/5 times 3.9 minus 4 plus 5. But what is this? This is going to be 0.1. Yeah, so let's see. 3/5 is 0.6, right? So we have 0.6 times 0.1 plus 4/5 is 0.8, and then times, this is going to be minus 0.1, and then I'm going to add 5, like that. Okay, so what is this? Well, this is just going to be 0.06 minus 0.08 plus 5. Okay, and so what is that? That's going to be minus 2/100 from 5, so that's going to be 4.98. So this number is approximately 4.98. And I would encourage you to get out your calculator and be amazed at how accurate this linear approximation actually is.